Hello, this is Professor Kevin Perry from the University of Utah, and the focus of my talk today is going to be on linkages between the Great Salt Lake and air quality. As many of you know, the Great Salt Lake is a terminal basin lake, and it has been shrinking over the past few decades, and it now is having impacts on air quality, which will be discussed in this talk. But to put this into some perspective, let's look at other terminal basin lakes around the world. So, for example, here is a satellite imagery of the Aral Sea, which is in Kazakhstan and Uzbekistan. In 1989, the Aral Sea was a very large freshwater lake, and it had a fishery and thousands of people which depended upon the fishery for their economy. By 2014, much of the lake had been desiccated due to water diversion. Uzbekistan is using a lot of the water from the main tributary stream to grow cotton in the desert. And they managed to dry up the Aral Sea. It started causing air quality issues. It even changed the local climate, making the area hotter during the summer. But the Aral Sea is not the only terminal basin lake to undergo this pattern of desiccation. Here we have Lake Urmia in Iran. In 1998, you can see that it was a very large freshwater lake, and by June of 2014, it had largely become desiccated and saltwater, and basically not usable for potable water anymore at that point, and it's in danger of drying up once again due to water diversion. If we look at Lake Pupu in Bolivia, you can see the same sort of pattern where this lake from 1986 to 2016, that 30-year period, has largely desiccated and has decreased in size by at least half. The Salton Sea in Southern California is undergoing a similar pattern. The Salton Sea was a lake that was created by mistake in the early 1900s when the Colorado River was accidentally unleashed into this basin, and it created a lake which didn't exist before. The tributaries have now been cut off, and the water is being used for other purposes in California, and the Salton Sea is starting to desiccate. So we can see where it was in 2003, which is the dark red line out on the edge, and then we have projections on essentially where it's going to go by 2047, and it's definitely decreasing. Owens Lake in California was a large lake before 1913, and the city of Los Angeles decided to divert all of the water for municipal purposes, and so they purposely dried up Owens Lake in California, and we now refer to this area as Owens Lake. So Owens Dry Lake in California is a hodgepodge of salts and minerals that are up on the surface, and it is one of the largest sources of particulate matter to the atmosphere in North America. So these dust storms that come off of Owens Lake have high concentrations of arsenic, high concentrations of PM10. It's a violation of the National Ambient Air Quality Standards. And because Los Angeles was the municipality responsible for desiccating the Owens Dry Lake, they're the ones that are responsible for trying to pay to mitigate the air quality problems caused by the dry lake. To date, they spent more than $2 billion on mitigation strategies, none of which have been particularly successful. And 15% of the taxpayers' water bills in Los Angeles County are going strictly for mitigation purposes at Owens Dry Lake. Here we have a video of dust storms coming off of Owens Dry Lake, and you can see that these dust storms are quite impressive. So here is a satellite image of the Great Salt Lake in December of 1984. This had been preceded by several years in a row of record-breaking snowpack in the Wasatch Mountains, and the lake filled to capacity. This image is at a lake elevation of 4,208 feet. It eventually peaked about 3 feet higher than this in April of 1987. They actually had to build pumps to push this water out into the evaporation basin off to the left in order to avoid flooding along the I-80 interstate on the southern portion of the lake itself. So at the time, it was the fourth largest terminal lake in the world. But though you can see the peak of that lake in the late 1980s, where it peaked over 4,210 feet. But if you look at the long-term lake elevation over the last 170 years, you can see that the lake has been decreasing over that time period, with some wet periods where it temporarily rises and some dry periods when it temporarily goes down. But over the long term, it has been decreasing at a rate of about 0.5 feet per decade. One of the things that we have that is putting a potential stress on the lake is water diversions from the Great Salt Lake. The primary sources of fresh water to the Great Salt Lake are the Provo and Jordan rivers on the southern part. We have the Weber River kind of in the mid-lake, and the largest source is the Bear River, which basically emanates from kind of the Bear Lake region in northern Utah and southern Idaho. The Bear River then moves up into Idaho and then curves around and comes back to the Great Salt Lake. The declines in the Great Salt Lake are due to a combination of water diversions and drought and some potential impact from climate change. The current status is that the lake is basically been desiccated. There's only 48% of the average volume, and there's more than 750 square miles of exposed lake bed. The Bear River Development Project is a project which is planning to divert even more water from the Bear River watershed so that it can be used for municipal and industrial purposes. It's anticipated to be a $2.5 billion project that will construct 3 dams on the Bear River and construct a pipeline to move that water down towards so residents along the Wasatch Front can use it. They anticipate diverting an extra 220,000 acre-feet of water and storing up to basically about a year and a half worth of water diversion in these reservoirs. The impacts would be a reduced inflow into the Great Salt Lake by an additional 20%. And another lake level decline of an additional 2 to 4 feet. It'll dry up tens of thousands of acres of shoreland wetlands and will increase the water rates as we have to pay for those $2.5 billion in infrastructure costs. So here we have, once again, a picture of the lake from December of 2016 when it's elevation high. But it's changed quite a bit. We no longer have, it's no longer a theory that dust from the exposed portions of the Great Salt Lake can cause poor air quality. Here's an example of dust in the air on April 14th of 2015 of dust that came from the Great Salt Lake. It led to a air quality index of 300, which was basically 3 times the unhealthy limit for So what conditions are favorable for dust production in the first place? Well, the first thing is that you need a high fraction of fine soil, basically silt and clay. The larger particles, the sand particles in the soil, will largely fall back down relatively quickly, but it's the small particles in the soil distribution that are most likely to remain in the atmosphere. The other thing is we need a weak, non-existent, or disturbed surface crust. The lakebed, much of the lakebed has a crust on it, which actually protects it from wind erosion. In places where that crust is breaking apart or where it doesn't exist at all, those are the places that might be places for wind erosion. Vegetation also slows down the wind speed and will reduce the amount of dust that is generated from a given area. So we have those, three things that have to do with the dust production areas themselves. But in order to actually get dust production, the soil itself has to be dry, and we have to have strong winds. And these are the meteorological conditions that can lead to dust production in areas that are prone to it. The strong winds can be generated by frontal passages, cold fronts in particular. It can be generated on a smaller scale from thunderstorm outflow. And on an even smaller scale, we have dust devils, which can generate dust off of the exposed portions of the lake. So here's what I did. I divided the lakebed up into 10 decision units, and each decision unit was further divided into smaller subunits. Each subunit was intended to be about a 4 kilometer by 4 kilometer box, making it 16 square kilometers. And when I did this, it ended up being a total of 122 subunits for coverage of the entire exposed portion of the Great Salt Lake. So in order to eliminate sampling bias, I put together a pre-planned gridded pattern for all the soil samples in a given subunit. So here we're looking at the southern portion of Antelope Island and the lake bed that surrounds it. And you can see that this has been divided up. This is all part of decision unit number 2. And we have subunits that are there. And each of those subunits have a grid spacing of about 500 meters. And surface soil samples from the top 1 centimeter of each grid point were collected and composited into a single bag. So we've essentially collected soil, for example, on like DU2, SU5 up in the upper part. It looks like about 64 sample locations were in that subunit, and we took a little bit of soil from each one of those locations, composited into a single bag for analysis to try and make it representative. How did I do this? I did it with what I call the University of Utah Dust Devil, which was basically a bicycle and a trailer. Why would I do it this way? Well, the cost was low, and you have a relatively low impact on the surface. On the right, you can see ATV tracks, where somebody had taken an ATV out onto the lake bed. And then in the middle of the ATV tracks, you can see the tire tracks from my bicycle. And you can see that I do a lot less damage to the playa. The other advantage of the bicycle is that you typically won't get stuck, although it is possible to get the thing stuck if you go out on a day and happen to encounter some mud out there. You can get it stuck. This one took me about 20 minutes to get out of. Going slowly allows you to do careful observations. The disadvantages, of course, is that there's 750 square miles, and the bicycle, you can only move 2 or 3 miles an hour out on the surface. It's physically challenging, and you have to wait at least 5 days after a rain event to let the playa dry out so that it's actually rideable. Why not use ATVs? Well, here's why. I was actually forced to use a ATV on the military range that is controlled. This is controlled by the military. They actually do live fire out on this area, and they didn't want to let me go out there because they were concerned about unexploded ordnance. And so they decided to accompany me, and they made me go on an ATV, and it was great for the first hour and a half. We covered a lot of ground, but we got stuck, and then we spent the next 8 hours trying to dig out, and you can see the incredible damage that we did to the playa. So the disadvantages of the ATVs is that it's expensive. It requires multiple people and multiple vehicles to extract. If you get stuck, it actually took 2 other ATVs to pull this one out. Can obviously cause significant damage to the playa, and it's really difficult to carefully observe the playa at high speeds. This field work was conducted between June of 2016 and August of 2018. I spent at least 122 days of soil sampling out on the Great Salt Lake. I bicycled over 2,300 miles. It took samples from all 757 square miles of the exposed lake bed. I took over 5,000 soil samples, which were composited into 122 samples. I took surface crust observations at every one of those 5,000 plus locations, and I brought back just a little bit short of 3 tons of soil to the lab for analysis. The laboratory analysis, basically we dried all of the samples for 24 hours and then sieved the soil into 9 size fractions. The smallest size fraction, the particles that were smaller than 75 microns, were then resuspended in a resuspension chamber, and the respirable fraction, the PM10 fraction, were then collected onto either Teflon filters or mylar substrates for subsequent analysis. The PM10 soil was analyzed by a combination of ICP-MS and synchrotron X-ray fluorescence to provide concentration measurements of 53 different elements. What we're looking at here is the percent of the bulk soil that was in the silt and clay size fractions. So what you're looking at is the areas on the eastern part of the lake in Farmington Bay had more than 10% silt and clay, which means that basically 10% of the bulk soil was in a size fraction that could actually be lofted by wind erosion. In comparison, if you look on the western side of Antelope Island, where the colors are basically black, less than 1% of the bulk soil was in the silt and clay fraction, which means that 99% of that material was sand, and sand will not blow very far from its source. So you can see that there are very big differences in the parent soils of the different areas. The eastern side of Farmington Bay has a high silt and clay content because that's where the Jordan and the river and the Weber rivers bring silt into the system. There are no large freshwater rivers flowing in to the western side of the lake, and it has a much higher sand content rather than silt and clay content. If we look at the northern half of the Great Salt Lake, you can see in the eastern side, or the right-hand side of this figure, we have the Bear River coming into the Great Salt Lake, and there's a lot of silt and clay being deposited by the Bear River. But most of the Great Salt Lake on the northern half has very low concentrations of silt and clay, with the exception of the extreme northwestern quadrant on the upper left-hand figure, part of the figure. So what type of surface conditions observations did I make at each of those 5,000 locations? Well, identified how much vegetation coverage there was, and then identified how thick the surface crust was at each of those locations. I identified it as either thick crust, which is greater than 1 centimeter, moderate crust between 0.5 centimeter and 1 centimeter, a shallow crust less than 0.5 centimeters thick, or areas that had no crust. I also identified a lot of different kinds of features that were on the surface, including cobbles, pebbles, granules, bioherms, which are kind of like stromatolites. There are some places where there's biological material that has created a crust, and we refer to those as biomats. There are sand dunes, there are dried mud polygons, there are gypsum crystals on the surface, and there are also rocks. that spontaneously move under certain meteorological conditions out on the lake bed and leave a trail in the playa. You might be familiar with the racetrack playa in Death Valley National Park. It was the first place in the world where this phenomenon was observed. There they had really large boulders that would move around. There aren't any evidence of large boulders moving around on the Great Salt Lake, but I did see at least 50 to 60 examples of rocks as large as a football moving around on the Great Salt Lake and leaving these trails in the playa. And I believe it's only the third place in the world where this has been observed. So, what does thick crust look like? Well, here's a picture of eroding thick crust. There is no intact thick crust out on the Great Salt Lake. If the thick crust exists, it's in an eroding state, kind of like this, where you can go out and you can pick up these large pieces. They're really strong, kind of like a dinner plate, and they protect the surface underneath from wind erosion. Here's another example of an eroding thick crust. These are really hard surfaces. You could drive a truck across these things without causing any damage, but there's not a lot of that, even that eroding thick crust out on the Great Salt Lake. Here's an example of those eroding dried mud polygons. These are seasonal in that when they become wetted, they basically reform, seal all the cracks, and then when they dry out, the cracks form themselves. These dried mud polygons in this particular location were about 3 inches deep, and I pulled one out here so that you could see the perspective of that. And this is another example of an erodible thick crust. The same sort of thing happens on a smaller scale with an erodible moderate crust. And remember, for a moderate crust, the surface there is between 0.5 centimeter and 1 centimeter thick. This is much more fragile than that eroding thick crust. Here's another example of an erodible moderate crust. You can see that the edges are curling up, and if you step on those, you'll essentially break off those edges. And you can see that that erosion process is occurring. A shallow crust is the most common type of crust that's out on the Great Salt Lake, and this one happens to be a shallow crust with really small granules on the surface. Interestingly enough, if you look closely in the background, you can see an actual dust storm caused by some outflow from a thunderstorm over that direction, generating some dust from the surface. The shallow crust is really thin, it's really fragile, and here you can see an example where I peeled it up so you could see how thin it really is. And here's an example of an actively eroding shallow crust where you have these mud curls that are drying up, and when the wind comes along, it will actually start to dislodge and displace these curls. And then the moving curls will dislodge other curls, and it will lead to more wind erosion over a larger area as these things break down. And then there are some areas out in the lake where there's no crust at all. This happens to be kind of a sand dune area out on the Great Salt Lake, and there's a little bit of vegetation kind of holding the sand in place, but for the most part, it's vegetation free. I didn't like these areas very much because, you know, imagine trying to ride a bicycle on a beach. It's not very fun. Here's another example of sand dunes that are out on the Great Salt Lake playa. And here's an example of a non-natural area. This area has been, the surface crust has been completely destroyed by ATVs. This happens to be an area where the brine shrimpers actually traverse quite often, and the crust has been completely destroyed in this area. So to summarize my findings, basically 67% of the entire lake bed is covered by an intact shallow crust. 1.5% is covered by an intact kind of thick crust. 4.2% is covered by an intact moderate crust, and 26.6% of the lakebed either has no crust or an erodible crust of various thicknesses. So I referred to those areas, that essentially quarter of the lakebed, as the areas with potential hotspots. So these are places where the crust is eroding or there is no crust at all. Vegetation, if you recall, is one of the things that can help reduce dust. And there's a lot of different type of vegetation out on the Great Salt Lake bed. This is an area that is being revegetated by bushes. Here's an area that is being revegetated by smaller vegetation. Not my area of expertise. Here's an area that's a combination of grasses and a tree in this case. Here's an area that is being revegetated by grass. And here's an area that's been completely revegetated by grass. This just happens to be in a time of the year during the summer when it's really dry and the grass is brown. But you wouldn't expect this. I certainly didn't expect to go out onto the lake bed and have it be completely vegetated in areas. But that obviously reduces the potential for dust erosion from that region. And then there's the Phragmites. Oh my gosh. Now, what are Phragmites? Phragmites are these large plants, extremely dense, almost like sugarcane. They're 10 to 15 feet high, and they basically make an impenetrable wall. Phragmites are an invasive plant. It was actually an ornamental plant from Asia that actually got away from somebody's house or garden and has started taking over the eastern shore of the Great Salt Lake. This is a place where Utah actually was blazing a trail through with a bulldozer, but it allows you to see how impenetrable this barrier actually is. So to summarize the lakebed vegetation, 15% of the exposed lakebed has some type of vegetation on it, of various either slightly vegetated or completely vegetated, some variation of that. 85% of the exposed lakebed is currently vegetation free. So where is that vegetation located? Now what I'm referring to here is non-Phragmites, because I obviously didn't take samples or observations in the areas of the Phragmites. So these are vegetation areas that are not associated with Phragmites. And in the southern half of the lakebed, you can see that we have a lot of vegetation beyond the Phragmites on the eastern side of the lake. There is also on the western side, we have Carrington Island, and there's an area over there on the western side where we're starting to have a lot of revegetation as well. The difference in the colors, the red circles are areas where vegetation is essentially holding in silt and clay, where it would be a dust source if there wasn't vegetation. And the green areas are places where there's a crust intact that is already protected, and the vegetation just adds extra protection to that. If we look at the northern half of the lake, most of the vegetation on the northern half of the lake is in the Bear River Bay on the northeastern side of this figure, where the vegetation is starting to encroach from the margins towards the Bear River. The other side, the western side, the northwestern side of the lake, is very sparse in terms of vegetation. The lake is extremely salty up there, and there's a lot of salt that remains on the playa, and that is not amenable to vegetation because it's too salty for most of the vegetation to thrive. So, what did I use for my dust hotspot criteria? Well, the areas that I think are the dust sources have erodible shallow crust or no crust, little or no vegetation, and have a visible dust plume when I disturb the surface by kicking it. Basically, that helps indicate the higher concentrations of silt and clay. So what does a dust hotspot look like? So here's an example of a dust hotspot that is eroding away. It has, in this case, an extremely shallow crust that is eroding. Once that crust erodes, then it exposes the fine material underneath to the wind. That can then move it around. Here's an example of where several of those dust hotspots have merged, and this is a dust hotspot region where dust can come from this larger region. These are fairly rare out on the lake bed. Most of the dust hotspots are more isolated, and this just happens to be a larger region. There are other dust hotspots. This is an area where we have a lot of those mud curls, and this entire area will start to blow when the wind picks up. If you pay close attention, you might notice that the color of the bicycle changed from red to blue. My first bicycle actually was destroyed by the salt, and I had to start using a second bicycle. So where are these dust hotspots located? So these are the areas with no crust or an eroding shallow crust and little or no vegetation. So in the eastern side, we can see that there's an area near where the Jordan River comes in on either side of the Jordan River, where we do have dust hotspots in Farmington Bay. We also, on the western side, also have a pocket of dust hotspots near Carrington Bay, and this happens to be close to the U.S. Magnesium Superfund site, which is a place where there's significant local contamination from an industrial process. In the northern part, there is a significant dust source near where the Bear River comes into the Great Salt Lake ecosystem, and then in the extreme northwestern corner of the lake bed in Gunnison Bay, way up in the northwestern part, is another area where there's dust sources. And there's much of the northern part of the lake is not a dust source. So to summarize my first goal, these dust hotspots have been located and they exist in all four quadrants of the lake. Only about 9% of the exposed lake bed currently generates dust plumes because it's protected by either a crust or vegetation. And the maximum amount of the lake bed which could act as a dust source if you removed the protective crust would be 22%. So luckily, the Great Salt Lake is dominated by sand. If it was dominated by silt and clay, we would have a much bigger dust problem than we currently have. So moving on to the second goal of this project was to determine how fluctuating lake levels might impact future dust production from the Great Salt Lake. So luckily in 2016, the state of Utah contracted with a company to create a very high resolution digital elevation model of the exposed portions of the Great Salt Lake. And what they did is they flew an airplane over the lake bed with a laser beam pointed down. This is called LIDAR, and they used it to measure the elevation every meter on the exposed lake bed. And we're going to look at Farmington Bay at first. And what I've done is I've actually combined the location of all of those dust hotspots with the LIDAR data to determine the elevation of every single one of the dust hotspots out on the Great Salt Lake. And what we're looking at here is the Great Salt Lake elevation on the x-axis, ranging from 4,192 feet all the way up to 4,210 feet. And on the y-axis, we have the fraction of the hotspots that would be covered by water at a given lake elevation. So, for example, right now, we have 100% of the lake bed is essentially exposed. If the lake were to rise to 4,198 feet in this region, so that's an increase of about 5 feet from where it currently is, that would cover up about 45% of the dust hotspots that I saw. If you want to get to 80% coverage, you need to go up to about 4,200.5 feet. And to cover up all of the dust hotspots that I observed, the lake would have to rise to 4,202 feet. This linear relationship was unexpected, but it's a very strong relationship. It has an R-squared of 0.998, which means that it's a very good linear relationship. And the slope on this regression line is 0.138, which means that for every foot change in elevation of the lake, either up or down, you increase or decrease the number of dust hotspots by 13.8%. So this information gives the managers of the ecosystem hard data that they can use to determine how fluctuating lake levels will impact dust production from the exposed portions of the Great Salt Lake. And that's information that they've never had before. So keep this in mind. This is for Farmington Bay. We're now going to move to Bear River Bay and see if the same sort of relationship exists. And for Bear River Bay, you'll see that there is also a linear relationship. It's not quite as good. It's R-squared of 0.96. And the slope is actually pretty similar. It's 12.8% per foot. But you'll notice that the entire line has been shifted significantly to the right. In this case, most of the dust hotspots were located at a higher elevation than those in Farmington Bay. And if you wanted to eliminate 50% of the dust hotspots in the Bear River Bay area, you would have to increase the lake level all the way up to 4,204 feet, which is about 10 feet higher than the lake is right now. And to get complete elimination of the dust sources, you'd have to go all the way up to about 4,207 feet, which is about 14 feet higher than the lake is right now. So that's going to be very difficult to mitigate with water. If we look at Gilbert Bay, which is the southwestern quadrant of the lake, once again, we have this linear relationship, R-squared of 0.98. This time the slope is about 11.7% per foot. If you want to eliminate 50% of the dust hotspots, you have to go up to 4,200.5. And if you want to eliminate all of the dust hotspots, you basically need to go up to about 4,206 feet. Moving on to Gunnison Bay, which is the extreme northwestern quadrant of the lake. Here we have a difference. We still have a linear relationship, but the slope is significantly lower. In this case, it's only 7.3% per foot. And if you want to eliminate 50% of the dust hotspots, you have to go to 4,202 feet. And if you wanted to eliminate all the dust hotspots, you basically have to fill the lake up again all the way to 4,210 feet, which is very close to what it was at its maximum back in the 1980s. So what will the snowpack do this current year? So what we have here is the SNOWTEL current snow water equivalent for the state of Utah for March 25th of 2020. And what this is basically showing is that we have an average snowpack over most of Utah, and certainly all of Utah, which is contributing to the Bear River, the Weaver River, and the Jordan River. The Uintas are slightly above normal with 111% of normal in that area, but we're not having a really large year for snowpack, which means that we're not going to get, we're just going to get an average amount of runoff into the Great Salt Lake. What we're looking at here is the elevation of the Great Salt Lake over the last 4 years. you'll see that there's an annual cycle in the elevation of the Great Salt Lake. It basically starts to increase in January and will continue to increase all the way through May or early June. And then that is basically either precipitation directly to the lake or melting snowpack, which causes the lake elevation to increase. And then, starting in late June and early July, the lake will start to decrease from evaporation. And it will continue to evaporate all summer and into the early fall. And the lowest lake concentrations are typically observed in October and November of each year. So if you look back to 2017, which was a pretty good snowpack year, we ended up with a 3.5 foot gain in the lake from a good snowpack year. And then in the subsequent summer, we lost 2 feet due to evaporation. The next year in 2018 was essentially an average snowpack year, and the lake gained about 2 feet. And it was a hotter than normal summer, and we ended up losing 3 feet due to evaporation. 2019 was an above average snowpack year. The lake gained 3 feet, and then we lost our 2 feet through evaporation. And this year we've gained about 1.5 feet, and we have an average snowpack, so we can anticipate another probably foot gain in the lake before the evaporation occurs. And that's essentially what we've seen over the last 4 years. So here's an image of the lake from last summer, August 28th of 2019. The lake elevation is 4,193.5 feet. And you can see that there's a significant amount of playa, that's 757 square miles. In the northern part of the lake, you can see that right near the edge of the pink water, which is definitely a pink color due to certain types of bacteria or algae that are, I think it's cyanobacteria, I think, that are up there. Maybe not cyanobacteria, there's a special kind, sorry. But you'll see a white ring, kind of like a bathtub ring. That's salt that is precipitating out of the lake bed, or out of the water. And this is what that looks like. It is a really hard crust of salt that is not prone to wind erosion. And that is what's happening in the northern part of the lake as it evaporates further. So to summarize goal number 2, the number of dust hotspots varies linearly with lake elevation. The number of dust hotspots will increase in Gilbert Bay and the southwestern portion of the lake if it continues to decline. But the number of dust hotspots is unlikely to increase in either the Gunnison Bay due to the salt crusts, to Bear River Bay because it's already pretty much completely exposed, or in Farmington Bay because it's also pretty much already completely exposed. Farmington Bay is actually the easiest area to mitigate with water because the lake elevations don't have to be nearly as high to cover up those dust hotspots. It also has the greatest slope of 13.5% per foot, and you can get 80% mitigation of the dust with a lake level of 4,200 feet. Gilbert Bay, you can get 80% mitigation at 4,202.5 feet. And 80% mitigation in the Bear River Bay takes a lot more water, and Gunnison Bay takes even more water than that. The third goal of my project was to determine if there are harmful heavy metals in the dust that might pose a threat to human health. And I'm just going to quickly summarize and go right to the findings. And that arsenic was the only element for which all of the measured values exceeded the recommendation values from the Environmental Protection Agency for both residential exposure and industrial exposure. There were 3 elements that exceeded the residential but not the industrial, and that was lanthanum, lithium, and zirconium. And there were 5 elements that had some values which exceeded the residential but not the industrial. And that was cobalt, copper, manganese, antimony, and vanadium. So I refer to these 9 elements as the elements of potential concern It doesn't necessarily mean that they're hazardous, because the EPA makes assumptions about how frequently people are exposed to the dust. And they make really conservative assumptions. So they assume that people will be exposed to the dust more than 200 days a year. In reality, it's going to be significantly less than that, but we don't know how much less than that. So what we need to do now is to determine how many days a year people are actually exposed to the dust. And once we have that frequency of exposure, then we can determine the dose that people are likely to receive, and then we can determine whether or not these heavy metals actually pose a hazard to the people who live along the Wasatch Front. And that's ongoing research that needs to be completed moving forward. I'd like to thank all of the public and private landowners who granted permission for me to cross their property to access the lakebed. This included the Hill Air Force Base, the state park, different mineral companies, Deseret Land and Livestock, Rio Tinto Copper, and Union Pacific was also very nice that they let me use some of their access roads. So I really appreciate that. And here's a picture of me out on the lakebed. It's getting late. I need to get off the lakebed in a hurry because it's going to be dark before long, but it made for an interesting photo. And we'll deal with questions offline. Thanks a lot.